Hello everyone, today I am going to give the introduction of bipolar junction transistor. Under this, I am going to explain about the basic construction of the bipolar junction transistor and the terminals of bipolar junction transistor and the junctions of bipolar transistor. Okay, now I will consider here the introduction to the bipolar transistor, that is the BJT. Okay, so the BJT or bipolar transistor was invented by John Bardeen, Walter Brattain and William Shockley in 1948 in Bell Laboratories. So these three scientists was invented our bipolar junction transistor. Okay, so here we have what is transistor means. First we have to know what is transistor means. Transistor means transfer plus resistor. Okay, this means transfer of current or a signal from one resistance to the another resistance. So that's why it is called as what? The transistor. Right? So that is what here transistor means, transfer plus resistance, that is transfer of current or signals from one resistance path to the another resistance path. Okay, so this is about what is meant by transistor. Now here we'll go with actual bipolar junction transistor. So bipolar junction transistor is a three-terminal device. It consists of PNP and NPN layers. Okay, so the BJT is a three-terminal device. Bipolar junction transistor is a three-terminal device. It consists of three terminals, and before that we have it consists of three layers. Okay, so the bipolar junction transistor consists of three layers and three terminals and two junctions here. We have two junctions. Okay, so three layers means that is two P layers and one N layer, or we have another one is also there, two N layers and one P layer. Okay, so that means if you consider any BJT, it consists of three layers. We have what we will see here, and it consists of three terminals. Okay, that is emitter, base, collector. We will see that, and it consists of two junctions, that is emitter junction and collector junction. Okay, so here we have two P, N layers, or two N, one P layer. Right, so one N layer and two P layers, or another one is two N layers and one P layer. So combinedly here we have any configuration, that is NPN or PNP transistors of BJT consist of three layers completely. So that is what about three layers we have. And next what? Three terminals. So here we have three terminals. Those are emitter, base and collector. We can represent here short form, and I will explain what is emitter and what is base and what is collector and all those things. Okay, and we have the two junctions, that is emitter junction and another one is collector junctions. Okay, so this is about briefly about the BJT and what we are going to study here. Right, so here we have two types of BJT. I already told that BJT is a three-terminal device. Okay, so here we have two types of BJTs, that is NPN. So here two N layers, one P layer, that is consisted by NPN transistor. Now we have here PNP transistor. It consists of two P layers and one layer. Completely it consists of three layers. So if you observe this BJT, both in NPN and PNP transistors, it consists of three layers. Okay, now what is the construction here? What is the construction of this BJT? Okay, so now we have PNP transistor and NPN transistor. Right, so here how we can construct this BJT? That means what? Here if you consider a single silicon crystal of germanium or silicon, and if you place a P-type material between two N-type materials, that will form NPN transistor, or we can also form PNP transistor by placing an N-type material between two P-type materials. Okay, so that is about the formation of PNP and NPN transistors. And here I will explain here how you can form a PNP transistor. Suppose this one is the single silicon crystal. Okay, on this side, single silicon crystal, or I will consider an intrinsic semiconductor, that is of silicon. So in this side I will add the trivalent atoms, and in this side also I will add the trivalent atoms, and in the middle I will add the pentavalent atoms. So if you add for a intrinsic semiconductor trivalent atoms, means it will form the P-type material, and if you add pentavalent atoms, means it will form an N-type material. Okay, so therefore here I am taking this silicon bar on both sides. Okay, outer sides I am taking with I am adding acceptor atoms, and here I am adding the donor atoms, so that here this material will becomes P, and here also the material will becomes P, and here we have N. So another way also we can tell this construction of PNP transistor or NPN transistor. That is nothing but sandwiching of an N-type material between two P-type materials will form a PNP transistor. Okay, and here how we can form an NPN transistor? We can form an NPN transistor by sandwiching a P-type material between two N-type materials. So that will forms the NPN transistors. Okay, so this is the basic construction we have for PNP transistor and at the same time an NPN transistor. Okay, so now how we can form a PNP or NPN means here so sandwiching of P-type material between two N-type materials forms NPN transistor, forms NPN transistor. Similarly, we can also form a PNP transistor. How it will be? That is sandwiching of N-type material between two P-type materials forms PNP transistor. So here we have PNP and NPN, and I will form PNP transistor by sandwiching of N-type material between two P-type materials. So it will form a PNP transistor. In the reverse case, we can form NPN transistor. That is nothing but sandwiching of a P-type material between two N-type materials, that will form an NPN transistor. So this is the basic construction of this PNP transistor and NPN transistor. Now we have three terminals. So this is nothing but the three layers what we have in PNP transistor, two P layers and one N layer, and totally it is three layers. And similarly for NPN transistor also two N layers, in between them one P layer we have, so that will forms NPN transistor. Okay, so this is about the concept, that is the BJT will consist of three layers. Okay, now we'll go with how many terminals we have for bipolar junction transistor. We have three terminals, either it may be PNP transistor or NPN transistor. We have three terminals. One is emitter, another one is emitter E, second one is base, that is B, and third one is the collector, C. So these are the terminals, three terminals we have for the BJT terminals here. Right, for the BJT we have three terminals, that is nothing but one is emitter terminal, second one is base terminal, and third one is the collector terminal. Okay, so if you consider here for a PNP transistor, this first one, P layer, is called as emitter. The second one, the base, and the third one, third P layer is here. We have third layer is called as the collector. Okay, and here also for NPN transistor, the first N layer is called as emitter, and P layer is called as base, and the last N layer is called as what? Collector. Okay, so this is about the three terminals that we have in NPN or PNP transistors, or we can also call combinedly in BJT. Okay, so now we have here the emitter, base, and collector. Then what is their doping concentration? Doping concentration of each layer, and what is the size of each layer? We will see here, right? So here we have three terminals. Out of that, the emitter is heavily doped. Emitter is heavily doped, and base is lightly doped. Lightly doped, right? Base is lightly doped, and the final one is collector is moderately doped. Moderately doped, right? So this is the doping concentration of emitter, base, collector regions. So here we have in PNP, P and P. P layer is emitter, it is heavily doped, and N layer is base, so it is lightly doped. Again here we have P layer, the doping concentration is in between the base and emitter. Okay, so that is what the doping concentrations. Then what is the size here? It is doping concentrations. Doping concentrations of all the three regions or the three layers we have here. Okay. Now we will consider what are the sizes. Size of the three layers what we have, right? So the size of the collector is more. Okay, size of the collector size is large. Second one is emitter size or emitter width. Base width is very thin or small in size. Small in size. And the third one is emitter size is in between. Emitter size is in between the base and collector. So these are the sizes of our layers what we have for NPN transistor or PNP transistor. Now we have the doping concentration here, emitter. Okay, then why this emitter terminal or this first layer is called as the emitter and this one is called as the collector. Okay, so here emitter terminal means the first layer of PNP or NPN has to emit more carriers. Okay, more charge carriers. So here if you consider this PNP transistor, it has to emit more holes. If you consider this one as NPN transistor, it has to emit more electrons. So whatever it may be, here why this emitter is called as, this first layer of PNP or NPN is called as emitter means, and it is heavily doped means it has to emit many carriers, more number of carriers. So that's why it is heavily doped. Okay, so emitter is heavily doped because it has to emits more number of carriers, more carriers. So that's why emitter is heavily doped. Okay, Next, what we have, the base. Base is lightly doped and the collector is moderately doped. Okay. So here, why it is called as emitter means it is emitting the carriers. That's why it is called as emitter. Next, why this collector is called as collector. Okay. So whatever the emitter terminal or emitter layer that emits the carriers will collected by the collector terminal. Okay. Why this layer is called as collector means collector have to collect the carriers emitted by emitter terminal. Right? So here this layer is called as collector because whatever the carriers that are emitted from the emitter will be collected by this region or this layer. Okay, so that's why it is called as collector terminal. Okay, so emitter is heavily doped because it has to emit more amount of carriers. Okay, so what is the relation between this doping and more carriers? Means here, if the doping concentration is increases, the free electron concentration will be increases. Okay, if the doping concentration increases, free electron concentration will be increases. Because suppose if you add a pentavalent atom to an intrinsic semiconductor, so what happened here? So there will be a covalent bond will form between 4 neighboring atoms and 1 free electron will be there. So that is the free electron. If I increase that concentration, doping concentration to 10 phosphorus atoms, so what happened? 10 free electrons will be obtained. So therefore, if you add more amount of doping concentration, so more free electrons will be available so that it can emit more amount of or more number of carriers. Okay, so that's why it is called as emitter and it is heavily doped. Okay, and here whatever the electrons or holes that are emitted from the emitter will be passes through the base and they will reach the collector. Okay, so that is what here base, that is lightly doped. Okay, and collector is moderately doped. Right, so this is about the doping concentrations and why they called with that names. Okay, next we have the very important point, size of the each layer. Okay, so size of the layer is here, the collector size is very high. Okay, the collector size is very high because here whatever the electrons are here, holes will travel from emitter to the collector. Here the electrons will flows from the emitter to the collector through this base. Okay, so here more number of electrons are passing, that is emitted by the emitter through the base and they will collected by the collector. Okay, so what happened here? Why we consider large size here? Because I will give the best example for here. Suppose a small space is there, that is the space will be for 100 members. Okay, so if I increases that number to the 1000 members and for a small space, the space. So what happened to the room temperature there? The room temperature will be increases. Okay, because instead of 100 we are placing 1000 members. Okay, due to that here the temperature will be increases. You know that why the temperature increases means the carbon dioxide that is released, and because of that carbon dioxide, so the temperature will be increases. Similarly here more number of electrons are emitted. If you consider a small size per collector, what happened here? Because of flow of those electrons in this small or collection of those electrons in this small area will increases the temperature. Okay, suppose if you on a switch, the light will glow and there will be a heat generation because the current is flowing. The current is flowing means the electrons are flowing through that. Okay, so because of that what happened here, the heat will be generated. Similarly, it will connect more and more amount of charge carriers, then the heat of that temperature of that material will be increases. Temperature of that collector region will be increases. Okay, so if you give more amount of space for the collector, so all these whatever the electrons that are coming from this emitter will be occupied with more space. Okay, so because of that the temperature will be distributed, so the device cannot goes to damage. Okay, so that is what we have here. Why we will consider large size for the collector. Okay, here the size of the collector is very large and the size of the base is very thin, because whatever the electrons or the carriers that are emitted from the emitter will passes through the base and they have to go to the collector. So if the base width is very less or thin, then easily these electrons will travel into the collector. Okay, these electrons will easily travel to the collector from emitter by crossing the thin region of base. So that's why here the base width is very small. Okay, and the emitter width is in between the collector and the base. So this is about the three terminals, that is emitter terminal, base terminal and collector terminal, or we have emitter region, base region and collector region of NPN transistor and PNP transistor. Okay, whatever it may be here, the emitter size is, emitter doping concentration is very high and the collector size is very large, and the thin layer is nothing but the base layer and the lightly doped material is also a base layer. Okay, so this is about the NPN and PNP transistor terminals and the three layers and their properties. Okay, their doping concentrations and their sizes. Okay, so this is about the doping concentrations and the sizes of the three layers. So what we have discussed now is nothing but we have discussed about three layers, that is 2 p-type and 1 n-type in PNP and 2 n-type and 1 p-type in NPN, and 2, that means completely 3 layers. That's why it is called as transistor is a 3-layer device. So it consists of 3 layers. Right. So next what we have, I have considered here 3 terminals. So 3 terminals is also over and these 2 are over. Here we have the symbols of PNP transistor and NPN transistor. So the transistor symbol or the BJT symbol is this one, that is nothing but base, collector and emitter. So here this arrow mark is inside, we are representing at the emitter, because in PNP transistor the current flows into the transistor. That's why that arrow mark gives the inside flow of current. Similarly here we have NPN transistor. That NPN transistor we are representing the arrow mark on the emitter outside. Okay, here you can have outside, right, because here the current flow will be outside. Okay, outside of the emitter. That's why here arrow mark is represented outside. In this PNP transistor it is represented inside. So these are the 2 symbols, that is PNP transistor symbol and NPN transistor symbol, that consists of base, collector and emitter, and the current direction what we have represented on the emitter terminal. Okay, so these are the symbols of NPN and PNP transistors. Now what is final one we have is the junctions. Okay, here we have the transistor has 2 junctions. Okay, here we have 2 junctions. What are those 2 junctions? That is emitter junction and collector junction. Either NPN transistor or PNP transistor consists of 2 junctions. One is emitter junction and second one is collector junction. So here JE is emitter junction. Emitter junction, and here we have JC is collector junction. Collector junction. So here the BJT consists of 2 junctions. One is emitter junction JE that will be represented with, and next one is collector junction that is represented with JC. Okay, so if you observe, this is the PNP transistor. Here between P and N, that is emitter and base. This one is called as emitter and this one is called as base. Between emitter and base, the junction is formed, that is P and N junction, PN junction. So the junction is called as what? emitter junction, or we can also call it as emitter base junction. So emitter junction is also called as what? Emitter base junction. So this junction is called as, here we have emitter base junction. This junction is called as emitter base junction or emitter junction. Emitter junction. So the junction formed between the emitter and base is called as emitter to base junction or emitter junction. Next, what about the collector junction? Collector junction is formed between base and collector. Okay, so this JC is called as, here we have P, sorry. So here JC is called as the collector junction. Collector junction or collector to base junction. Collector to base junction. Okay, so if you observe this one, emitter to base junction, that is emitter junction, and another one is what? Collector to base junction. So or collector junction. So here the base is in the middle, and there will be a formation of two junctions with the base, that is emitter base junction, collector base junction. Okay, so here we have two junctions, that is between this we have one junction, and between N and P we have another junction in PNP transistor. So I have clearly indicated here, P is what? Emitter, N is what? Base. Similarly, N is what? Base, and P is what? Collector. Okay, so this one is the collector. So between base and emitter and base we have emitter junction. Between base and emitter, base and collector, or collector to base is nothing but collector junction. Okay, so like this we have two types of junctions, that is emitter base junction, and another one is collector to base junction or emitter junction or collector junction. So here we have JE and JC junctions, that is JE junction and another one is JC junction. So these are the two junctions what we have. Then how you can represent this PNP transistor or NPN transistor in two diode model. Okay, so here we have considered that one junction is PN junction. Okay, that emitter junction is here PN junction. P is what? Here the emitter, and N is what? The base. So if you consider any PN junction, here, it is PN junction, P and N is there. So this is the anode and this one is the cathode. So how you can represent this one? This one symbolically will represent with diode. Okay, so this one is anode and this one is cathode. The same notation I am going to use here. Okay, so here in the first junction we have PN formed between PN. So P is here. First we have to draw the emitter side is anode and cathode is at the base side. So that's why here I am representing emitter. This one is the base side. So it is anode and this one is cathode of first junction. Next what we have here, the starting one is what? N type, that is base and collector. So N means what? Here we represented, that is cathode. So that's why here I am representing this cathode. And this side we have the last one, collector side, we are representing with the anode. So this is what the back-to-back connection of this PNP transistor. And here this terminal is called as emitter and this terminal is called as collector. But in between the two junctions we have what? In the middle, that is base terminal. So this is the representation of PNP transistor back-to-back. Okay. Now we have another one, that is NPN transistor. NPN transistor also consists of two junctions, that is emitter junction and collector junction. Here the emitter junction is formed between N and P, that is emitter and base. Okay, so this emitter is N type, so I have to represent that one with cathode. And here we have the P type, so I have to represent that one with the positive value, positive terminal. So this one becomes PN and P junction representation here. And here we have another one, this is P and N. So P is anode and N is cathode, so I have represented that one. Okay, so this is what the back-to-back representation of our NPN transistor also. Okay, in two diode model. So here we have the base in the middle, right? So this is about the introduction to the bipolar transistor. Here we have the basic construction. Next one is the layers that are present, 3 layers, and we have 3 terminals and again 2 junctions and their representation in 2 diode model. Okay, so thank you for watching. Subscribe our channel.